Let's now look at all four of these chemical reactions and their mechanisms to try to determine what factors will actually influence the reaction products that are made. So typically, SN2 reactions compete with SN1 reactions, which together compete with E1 reactions, which together compete with E2 reactions. In other words, all of these reactions are competing with each other. There are 11 common factors that will help us predict which of these reaction mechanisms dominate and in turn help us predict which reaction products dominate. We can first look at the substrates, the alkyl halide, whether it's primary, secondary, or tertiary, what our leaving group is, whether my alkyl halide is conjugated or not, whether my alkyl halide is saturated or not. In other words, attached right to a vinyl or an allyl group. I can also look at the strength of my base, whether it's weak or strong, whether my base is bulky or not bulky. I can also look at my nucleophile strength, whether it's weak or strong, or whether my nucleophile is hindered or not. Another factor includes solvent, whether it's polar or nonpolar solvent, whether it's a protic or aprotic solvent, and also one common factor is actually temperature. Can we adjust the reaction temperature to favor one of these reactions over the other? Now let's look at the substrate and the alkyl halide, whether I have a primary, secondary, and tertiary alkyl halide. And let's just compare two at a time here. So let's first compare SN2 versus E2. Primary alkyl halides tend to undergo SN2 reactions very quickly, whereas tertiary alkyl halides only undergo elimination 2 reactions. It has a lot to do with the steric hindrance of the alkyl halide. If I look at the secondary alkyl halide, I need to adjust other parameters to favor either SN2 versus E2, like the strength of the base, the strength of the nucleophile, whether it's hindered or not. If I now compare SN1 and E1, just talking about whether I have a primary, secondary, or tertiary alkyl halides, typically, primary and secondary alkyl halides do not undergo SN1 or E1 reactions because they need to go through a carbocation intermediate, which is not very stable, especially for the primary alkyl halides. If I look at tertiary alkyl halides, they undergo both SN1 and E1 reactions, so I have to adjust other factors now if I want to differentiate between the two different reaction mechanisms for SN1 versus E1. Let's look at that same trend for SN2 versus E2 using some molecules here. If I have a primary alkyl halide, that carbon, the one that has the halogen attached to, is fairly open and I can have a nucleophile attack it. If I had a tertiary alkyl halide, my nucleophile couldn't get in. So primary alkyl halides react faster than secondary, react faster than tertiary, so I get the substitution product typically. In elimination reactions, I can remove any hydrogen that's adjacent here to form the elimination product. However, I'm always in competition with an SN2 reaction, and because primary alkyl halides react so fast with SN2, they don't get a chance to react with E2 reactions. Therefore, it's only the tertiary alkyl halides that I do elimination on. So tertiary have a greater rate than secondary, a greater rate than primary, because primary undergo SN2 reactions. Let's now look at leaving group. When we talk about substitution and elimination reactions in this chapter, we concentrated mostly on the halogens as leaving group. fluorine, chlorine, bromine, and iodine. If I started out at the top of the periodic chart and moved down the chart toward iodine, my electron cloud gets larger and larger. It is more polarizable, so it becomes a better leaving group because I can start to break that bond in its transition state, and so it's more reactive. And so iodine is a better leaving group than bromine, which is a better leaving group than chlorine, which is a better leaving group than fluorine because of polarizability and because of electronegativity. If I look at the reaction rates, we can actually see that that's true. If I set the reaction rates relative to each other, so I set fluorine relative at 1, the reaction rate of the iodo compound is 30,000 times as fast. Let's now look at conjugation. It turns out benzylic and allylic alkyl halides, they can undergo SN2 reactions, but they still need to be primary. So I have a primary benzylic or a primary allylic halide. They undergo SN2 reactions. Typical substitution reaction depending on the nucleophile and where the alkyl halide is. These same molecules can also undergo SN1 reactions, because if I were to lose a chlorine, my resulting carbocation is benzylic in this case, and I can show resonance stability. Therefore, SN1 reactions are favorable for benzylic and allylic alkyl halides because of resonance stability here. They can also undergo E2 reactions, especially if I have some way of stabilizing them. I have not only a tertiary alkyl halide here, I have benzylic. So once I eliminate that, I can form an allylic system or a conjugated system here, and that's stable. So if I form a stable product, that reaction mechanism is a favorable reaction mechanism. If I'm allylic, I'm one carbon away from a double bond, and I do an elimination reaction, I form a structure here which I can form a resonance structure with now, and that's going to be stable. So E2 reactions are also favorable for benzylic and allylic. And finally, conjugation for E1 reactions. These are also stable because they go through a carbocation. If I can form a stable carbocation, either by being highly substituted or being benzylic or allylic, that is a favorable reaction. So all 4 of these reactions are actually enhanced by being benzylic and allylic. What's the situation with a vanillic or arylic alkyl halide? If I look at this molecule down here, my chlorine is attached directly to my carbon-carbon double bond, and this one here is actually attached to a carbon with a carbon-carbon double bond. This one would be a vanillic, this one would be a arylic alkyl halide. It turns out this electron cloud is negative enough that it actually repels any nucleophile that will be coming in. So saturated alkyl halides, either vanillic or arylic, they do not undergo SN2 reactions. How about SN1 or E1 reactions? Both of these would go through a carbocation. So in both cases, whether I have a vanillic or arylic alkyl halide, if they lost the halogen to form the carbocation, that carbocation is unstable, and that arylic carbocation is unstable. So these 2 molecules do not undergo SN1 or E2 chemical reactions. Their intermediate is too unstable. It's an unfavorable chemical reaction. E2 reactions for vanillic and arylic are a different story. If I have a very, very strong base like sodium amide here, I can actually remove that proton here at the same time as my bromine leaves to form the alkyne. Notice this is an internal alkyne, because if I had a terminal alkyne, I would deprotonate it with the sodium amide itself. So I need a strong base. How about that base strength? If I look at certain alkyl halides, here is a secondary alkyl halide. This is a carboxylate, which is considered a weak base. I have 100% substitution reaction. So a weak base typically favors substitution, whereas a strong base typically favors elimination. So if I take the same alkyl halide and I put in ethoxide, I tend to favor the elimination reaction rather than the substitution reaction. If I have a tertiary alkyl halide and I have a weak base, they tend to favor either SN1 or E1 reactions, again solvolysis. So I tend to form both my SN1 product or my E1 product. If I have a strong base, I can't undergo an SN2 reaction here because that's tertiary, but the strong base tends to favor the elimination reaction. So I get nearly 100% elimination and nearly 0% of my substitution product. If I look at the structure of the base, if I have a non-bulky base, I tend to favor the elimination product, but only slightly over the substitution product. If I have a very bulky base, even with a primary alkyl halide, I tend to favor the elimination product over the substitution product. So steric hindrance favors elimination. Nucleophile strength. We've talked about strength a little bit in a previous video. Some of the most common ones are iodide, cyanide, or my hydroxide or my alkoxides here. Those are strong. My weak ones are my solvents. So strong nucleophiles favor SN2, where weak nucleophiles favor SN1 or solvolysis reaction. Let's just look at some nucleophile trends again. Hydroxide is a stronger nucleophile than its conjugate acid. The sulfhydride is a stronger nucleophile than the thiol, and the amide is a stronger nucleophile than the ammonia. That's because I have these charges on there, these lone pair electrons that are very reactive. I can also look at nucleophilicity as I go from left to right on a periodic chart, meaning electronegativity tends to hold on to electrons more. So fluorine is very electronegative, so it's a poor nucleophile. It doesn't want to attack anything, or hydroxide is willing to react. Same thing's true here with ammonia and water. Ammonia is a better nucleophile than the water, and my trimethylphosphine is a better nucleophile than my dimethyl sulfide. Also, nucleophilicity increases down a group, so iodine, which is polarizable, is more nucleophilic than bromine and chlorine because I can distort my electron cloud and get in there to attack that carbon. And the same trend would hold through if I went down from oxygen to sulfur to sulfide. Selenium. Selenium is a much better nucleophile, though we don't use that very often. If I look at the steric hindrance of a nucleophile, it follows very similar trends to that of a sterically hindered base. If I have a small non-hindered nucleophile, I tend to be able to react well with primary alkyl halides, and I get an appreciable amount of the substitution reaction, but it's still in competition with elimination. If I used a very sterically hindered nucleophile, in this case, I am going to get mostly elimination reactions. So if I want to do substitution, I'm going to use a small nucleophile rather than a large nucleophile. Solvent polarity is also a factor that will help us determine what our products are. If I look at a polar solvent, I can actually stabilize my resulting leaving group as it leaves. So if I can stabilize one of the products, that helps favor the products. I can also stabilize an intermediate here. If I use water again, which is a polar solvent, I can stabilize an intermediate like my carbocation, which would help for SN1 and E1 reactions. When we're looking at solvent polarity, we have to keep into account our reactants and our transition states and our products that are formed to determine whether a polar solvent will favor a product or not. So if the reactant is charged, it will tend to stabilize one reactant more than the other. And so for one reactant, I might have a much higher activation energy because I stabilize my product. Therefore, the polarity of the solvent could decrease the rate by having a more polar solvent. In another instances, if my solvent stabilizes my transition state, I'm actually lower the activation energy by using a polar solvent, and therefore I'm going to increase the rate of the chemical reaction. So I got to look at both, whether I have a charged reactants and I stabilize the reactants relative to each other, or if I have neutral reactants and I stabilize the charged intermediate. Let's now compare and contrast nucleophiles to bases and look at their strengths. Hydroxide is considered a strong base and a strong nucleophile, so I undergo elimination and substitution reactions. Alkoxides that are small are considered strong nucleophiles and strong bases, and amines that are deprotonated, that are small, those are also considered both strong bases and strong nucleophiles. If I look at a hindered alkoxide, those are actually considered weak nucleophiles because they're just too big, but very strong bases. And these amine-containing anions, they're considered weak nucleophiles but very strong bases, again because they're bulky. If I look at strong nucleophiles, these are typically ones that are either small but have lone pairs of electrons. So an amine is a strong nucleophile but a weak base. This sulfide is considered a strong nucleophile but a weak base. And the same thing's true with iodide, cyanide, and this nitrile anion. Those are considered strong nucleophiles. Again, they're small and linear. The carboxylates, a deprotonated carboxylic acid, are considered strong nucleophiles but weak bases. And finally, my sulfur-containing compounds with hydrogen on them, my thiols, those are considered strong nucleophiles and weak bases. And then weak. Those are my solvents. Those are the ones that undergo SN1 and E1 reactions, solvolysis. So if I put this all together, if I have strong base that is also a strong nucleophile, those tend to favor SN2 or E2 reactions. If I have a weak nucleophile but a very strong base, those tend to favor E2 reactions, and those are typically the bulky ones. If I have a strong nucleophile but a weak base, I can get exclusively SN1 as long as I'm working with a primary alkyl halide. And then finally, my weak nucleophile or weak acids, my solvents, they undergo both SN1 and E1 reactions, solvolysis. If we just look at SN1 and E1 reactions, in order to get from my reactant to the carbocation, I have to go through a transition state, and that transition state is polar, and so polar solvents will stabilize that transition state, and they will also stabilize my products. Let's look at some effects of solvent polarity. In this case, I'm using a mixed solvents to adjust the polarity, where if I have 100% ethanol, I'm considered mildly polar. But if I keep on adding more and more water to the ethanol till I get up to 100% water, that's considered very polar. I can see that has an effect on the reaction rates for an SN1 reaction. So if I set the relative reaction rates at 1 for 100% ethanol, my reaction rate is 1200 times as fast using 100% water. So solvent polarity has an effect on the reaction rates by stabilizing that transition state in my eventual carbocation. Okay. Solvent polarity also has an effect on SN2 and E2 reactions because they stabilize the transition state again. My transition state always has a polar component to it. I can actually stabilize that transition state a little bit. How about whether it's protic or aprotic? SN2 and E2 reactions should be carried out in polar aprotic solvents, just ones that are polar, whereas SN1 and E1 reactions should be carried out in polar protic solvents. The reason we use protic solvents for E1 and SN1 is because I can actually stabilize the resulting carbocation that is formed when my leaving group leaves on its own. And finally, temperature. High temperature favors elimination reactions. Elimination reactions actually form more products than reactants, so my enthalpy increases. Here I start with 2 reactants and I get 4 different products in this case. So I have a greater enthalpy which favors the product. So if I raise the temperature, I'm going to get more of the elimination reaction than the substitution reaction. Let's put together another chart, and you can go on the internet and find dozens and dozens of these charts which sort of put together the different criteria for the SN1, SN2, E1, and E2 reactions. If I look at methyl alkyl halides, they typically only undergo SN2 reactions. Primary alkyl halides that are unhindered, they undergo SN2 and E2 reactions. Primary alkyl halides that are hindered, they undergo E2 reactions. And then when I get down here to secondary and tertiary alkyl halides, I have a mixture. I have 3 different products that can form. Notice I do not undergo SN2 reactions down here. So I then need to look at my strength of my base and nucleophile. So if I have a strong base or a strong hindered base, I tend to favor elimination reactions. If I have weak base or weak nucleophile, I tend to favor first order reactions that go through carbocations, meaning my SN1 or E1 reactions. Sometimes we cannot predict a reaction that will yield one product, but there are some criteria that help us determine the major product. The strength of the nucleophile determines the order. Strong nucleophiles or bases promote SN2 or E2. Primary alkyl halides usually undergo just SN2 reactions. Tertiary alkyl halides give us a mixture of products, but they cannot undergo SN2 reactions. Higher temperatures favor elimination, and bulky bases favor elimination because they can't attack that carbon that is next to the hydrogen. So they attack the hydrogen instead.